right, I'm back. Let's get going. Questions today. So today's topic is Mergesort. This is another step on our journey in sorting algorithms. So what we've done so far is we've looked at a couple of iterative sorting algorithms, and those work, fairly straightforward way. We looked at bubble sort, which you can think of as sort of repeatedly fixing, making small changes to an array to fix items that are out of order. And, if I do that enough times over and over again, it actually really, if you think about it, really doesn't matter, if I go forward or backwards to the array, what order I go through the pairs. If I look at every pair of adjacent items in an array, and if I find a pair that's out of order and I switch them, and if I just repeat that process until there's a time that I go through the entire array and I don't find any pairs that are out of order, then that will, in fact, sort the array eventually. It's not a particularly great way of doing it, but it will work. The other approach that we looked at was insertion sort. And in insertion sort, it's kind of like, I start with an empty array, and the way that we did insertion sort is a little different than this, but you can think of insertion sort as starting with an empty array, and then one at a time taking a value from, an array that has values in it and moving it into the right spot in the sorted array. And so, if I take, like I said, it's sort of like people sort cards, right? I take a hand of cards and I sort of start moving them to the left. I keep the sorted part to the left, and if I kind of stick them all in the right spot as I'm doing that, eventually I go through all the unsorted items, insert them into the right spot, and I'm done. So these are both sorting algorithms that I think have some good intuition around them. Today what we're doing is we're looking at a different approach, which I think is kind of neat. It takes us back to looking at recursion because it eventually leads to a recursive algorithm. The idea here is that we're going to utilize this sort of fact about sorting or about arrays, which is that we can merge two arrays that are already sorted efficiently. I talked a little bit last time about how many sorting algorithms try to identify data that's already sorted, because if they can do that, if I can identify a chunk of sorted data and have another chunk of sorted data, merging those two together becomes quite simple. And one way to think about this is that if I know that if you give me two arrays and I know they're already sorted, at any given step, and I'm trying to kind of merge them together, in any given step, there's only two values that I need to consider. That value at the front of both arrays, so kind of the next value in both arrays. So I have array A that's sorted smallest to largest, array B that's sorted smallest to largest, and I want to merge them together. Step by step, the only value I need to look at in either array at any given point in my merge algorithm is the smallest value that's left in that array that I haven't moved into the merged array. And so because of this, every time when we've run these other sorting algorithms, we've had to kind of look, think about insertion sort. Every time I take a value and move it into the sorted part of my array, I potentially have to compare it against up to n other values. If I'm moving it, if I'm kind of swapping it in from the right, I have to start with the largest value and keep examining values until I find the right spot. When I'm merging, because I know the two arrays are already sorted, that's the trick that allows me to only focus my attention on the first element in either array at any given point in time. And so today's lesson walks through both merge visually and then goes through a programming example using the same idea. And so those are get us started. Now, once we have this method, so and tomorrow when we look at Quicksort, we're actually going to kind of do the opposite, because tomorrow's homework is implementing more of the, on some level, what I hope you'll notice today when you finish today's homework problem is that once you have a merge sort is actually quite straightforward. The idea here is that we treat this, so it's kind of like there's this chicken, we feel like there's this sort of chicken and an egg problem here, which is that I can create a sorted array very easily given two other sorted arrays, but where do I get those two other sorted arrays from? Where do they come from? And so there's this kind of like this process of trying to figure out, okay, well, this sounds great, but again, where do I get these two sorted arrays from? And this is one of these places where it's fun to think about things recursively. Because if I take a big array and I think about, okay, well, I can divide it in half, but those two halves are not sorted. And so I can't do merge sort yet, right? I can't do a merge, right? If I just take a big unsorted array and divide it into two parts, I can't yet do a merge because those two parts are not sorted. Okay, well, what if I keep applying this, right? So I take one of the smaller arrays and I divide it into two parts. Okay, they're probably still both too big to apply. I can't merge them yet because they're both unsorted. And the question is, if I continue this process, if I continue taking an array and making it smaller and smaller and smaller and smaller and smaller, at some point, is there an array that I'll find that will be sorted, right? And the answer is yes. And the reason is if I keep taking things and making them, tearing them in half, tearing them in half, tearing them in half, eventually I'm going to get to an array that has one item. And that array is sorted. An array with one item is sorted automatically. It doesn't matter what the item is, that array is sorted. And so now it's like I have this toehold in the problem, which is that I've observed that if I start, the other way to think about it is just to say, okay, well, if I start with an array that has size 1, I can merge it with another array that has size 1 in O(n) time. That's kind of cool. What do I get out of that? I get a sorted array of size 2, right? So now I can combine that sorted array of size 2 with another sorted array to make a bigger sorted array. And let's say I have, I start with, some number of elements. I pick 4 of them. I merge the two pairs into two arrays of size 2, and then I merge them together into one array of size 4. So I've sorted that array of size 4. All I have to do is run over to another part of the bigger array and do the same thing. And now I've got another array that's sorted of size 4, and I can sort those two, merge those two together into an array of size 8. And I can keep doing this in different parts of the array. And so what falls out of this is this very, very sort of cool recursive algorithm, whereby the way that we sort a large array using merge sort is that we break it down recursively into smaller and smaller arrays. And when we apply recursion on an array, in this particular model, what we're doing to create two smaller subproblems is we're dividing the array in half. So we take the array and we divide it into two pieces, and then we put those two pieces back together later. But if I take an array and I divide it in half, and I divide the halves and halves and the halves and halves and halves, eventually I get down to arrays of size 1, at which point I can start to merge things again. So the way that your recursive algorithm will work today, the base case, will be when you reach an array of size 1, or it turns out I think it's useful to handle the 0 case as well. An empty array is also sorted. Once I get to an array of size 1, I don't have to do any more work. I have found a sorted array, and the way that I combine the results from different steps is I use this merge method. And by combining those two together, I can essentially sort a large array efficiently. One of the things I'll point out, before I start taking questions is that, and this is something that, we're not going to approach mathematically in this course, I think you may later, is that you can prove that, so whenever we implement an algorithm, it's helpful to know what to expect. Like what kind of performance should we expect from an algorithm? And one of the things that theorists can help with here is they can give us bounds, like mathematical bounds. They can say, well, in the worst case, a sorted algorithm should do no worse than whatever. And it turns out that an optimal sorting algorithm should never do worse than O(n) log n performance. So this is kind of a new performance category we haven't seen before. And it means that the performance, it's not linear, right? O(n). So remember, just checking whether an array is sorted or not is O(n). That doesn't even do any work on trying to sort the array. So there's no way that I can sort an array in O(n) unless, for example, it's already sorted, in which case I'm done. But if I have work to do on the array, O(n) is the time it takes just to verify that the array is sorted. So we would expect our sorting algorithms to not be able to achieve O(n). O(n) squared, however, is the running time that we've seen in some of the sorting algorithms that we've looked at over the past couple days, like insertion sort and bubble sort. O(n) squared is worse than, so O(n) is unachievable. O(n) squared is inefficient. the bound that you can place on sorting algorithms is essentially O n log n. So an optimal sorting algorithm should not do worse than O n log n, no matter what inputs I give it. And that's the other interesting caveat here, right? So when we examine these algorithms, the algorithms that we looked at yesterday, for example, insertion sort, you might say, well, wait, hold on, insertion sort is O n if the array is sorted. But that's not how we evaluate the runtime in this type of situation. Worst case runtime, I'm allowed to pick any array and give it to you and you have to sort it. And it's the worst case runtime. So it's essentially the worst input to the method. And there are arrays for which insertion sort is O n squared. And there are arrays of inputs for which bubble sort is O n squared. And so those algorithms are not optimal because in certain cases they don't achieve the O n log n runtime. Merge sort, on the other hand, is optimal. So we go through the performance evaluation or the algorithm analysis here visually, which I think is actually really, this one has like a real beauty to it in terms of how it breaks down because of how you're dividing things and stuff like that. It's just kind of neat. And we show that merge sort is O n log n. So that's good. One of the downsides of merge sort is it takes a lot of space. And one of the other downsides of merge sort, you may have noticed this. So if you look at our merge method, that merge method, if you look at the code, it has no dependence on the inputs. It always is O n. So it's never better than O n. It's always O n. It's never worse than O n, but it's always O n. And so merge sort, worst case performance is O n log n. So it is an optimal sorting algorithm. But the problem with it, and the reason why it's not necessarily used everywhere, is that the best case, well, there's two problems with it. One is it requires a lot of extra space because I need essentially a whole another array potentially to store my intermediate results. It also never does better than O n log n. So if you give merge sort a sorted array, it'll still do n log n. If you give it a randomly sorted, like worst case performance, n log n. Best case performance, n log n. Average case performance, n log n, right? You can tweak the algorithm. I mean, you could say, well, why not just check if the array is sorted first and then if to return, and you could do that. But I'm talking about kind of the merge sort that we've implemented today, sort of the classic merge sort algorithm. The performance is always O n log n because it doesn't really look at the inputs as it's going. It's just kind of applying the same strategy. And there's something nice about that because it's quite predictable. But good, the sorting algorithms that are used in languages like by default in languages like Java and Python are more sophisticated, and one of the things that they're doing is they'll do no worse than n log n, but they should be able to do better in the average case, right? So given certain assumptions about the underlying data, like the data is almost sorted or consists of large sorted sections, more sophisticated algorithms can do better than O n log n on certain inputs. Merge sort will never do better than O n log n. It will always do n log n. So it's like extremely consistent, very reliable, but also has no, opportunity to do better, right? There's no way for it to outperform that. All right, questions about merge sort or about other sorting related things. We can look at sorting stuff. We could do merge, using a different approach. Anything is fair game. Questions on anything? I'm at your disposal for the next half an hour or so we can talk about whatever. Favorite sorting algorithm? I don't know. Good question. Um, I guess my favorite sorting algorithm is one that's built in to whatever language I'm using because I don't like to have to solve this type of problem on my own. Um, yeah, I mean, it's a great question. I mean, there's different types of programmers, and you know, I find myself maintaining a fair amount of code, and so I try to keep things simple when possible. I would not probably ever implement my own sorting algorithm, even if I wasn't happy with the default for some reason. I would probably just try to find a library that somebody had written that had different alternatives. Um, I mean, there's something attractive about a merge sort. I mean, I guess maybe you can start to think of like the sorting algorithms as almost having different personalities, right? You almost start to feel about like, you know, people you know that personify these sorting algorithms, right? So like bubble sort, I don't know if you've ever like met somebody and who's doing some type of task, and I've been this person before, so I'm not throwing shade at anyone, but they're doing it in a way that is correct, but is going to take a long time. You know, it's like it's not optimal. It will work, but sometimes there's some comfort in doing things that way, where it's like, you know, I feel like that's sort of bubble sort, right? Like bubble sort is sort of like the person who's like not taking a particularly sophisticated approach to solving a problem, but it'll work. You know, it's gonna take a while. You know, um, so yeah, merge sort. You know, I like the recursive aspects of merge sort. I think it ends up being the merge itself is pretty tedious. If you look at the code, I just feel like it's like not a particularly satisfying piece of code to write. Whatever, it'll work. The Quicksort, which we'll talk about tomorrow, is fun because it's unpredictable. It's like the wild child of the sorting algorithm category. Like it can have great performance, it can have terrible performance. So we'll talk again about Quicksort tomorrow. And Quicksort, in the best case, can achieve O(n) log n with only a small amount of extra space. So it improves on merge sort, but there are pathological cases for Quicksort where its performance is actually O(n) squared. So yeah, Quicksort's sort of all over the place, which is neat. You know, yeah, I mean, every time I go on the Wikipedia page and find a different sorting algorithm, they're all kind of cool, right? I mean, clearly this is a problem that people have thought about a lot, and there's all sorts of different approaches, and there's actually really neat sorting algorithms that you can use when the data has certain properties, and there's all these little like micro optimizations people have made. If you're sorting integers, you can look at the first digit and do things. There's something called radix sort, which is quite fast if you're sorting data with certain properties. So there's just still like a lot of neat tricks in this category, and it's such an important problem that, you know, you have these general purpose solutions and they have these really specialized solutions. Like for example, you know, I would love to try to teach Sort, which is the sort that's used by Java and Python, but it's actually really complicated. Like I've read through the description a couple times and I sort of get it, but I don't think I would trust myself to implement it because it is pretty sophisticated. So and that goes into the second question, which is another good one. You know, a lot of the optimizations, so this is my understanding, and again, if you the best way to answer this question, which is a great question, is to go and read up a little bit about Sort and see some of the techniques that they're using. So Sort is the sorting algorithm was introduced into Python in 2002, and now it's, I think, also in the Java standard library. I suspect that it's quite a bit of extra code to implement Sort on top of something like Mergesort. As far as I know, Sort also uses techniques drawn from Mergesort, drawn from Insertion Sort in certain places to sort small arrays or whatever. I think that one of the things about some of these modern sorting algorithms is they're trying to respond to features of real world data. So you think about the kind of things that programmers do with data and the way that affects how we sort it. So we talked a little bit about this before, where it's like, you know, it might be, you know, for example, I've written code like this, where it's like, I have one sorted array and another sorted array, and I slap them together and then sort them again. right? Now, the sorting algorithm doesn't know that there's two big sorted arrays in there. So in theory, that should be ON, right? Because if it knew, and a lot of times programmers will do this. They won't call merge. They'll just be like, just sort it again, right? Because they're thinking, I'm lazy and I just want to use the sorting algorithm. But the sorting algorithm is like, whoa, hold on. If you had told me that there were two sorted arrays here, that would have been super useful information because I would be almost done. And so again, TimSort seems like it's trying to actually do a fair amount of work to identify these sections of data that are already sorted, because that's really, really normal, right? Like, again, same thing. I've got some already sorted data. I throw some data at the end, and then I sort it again, right? I think if you look at one of the places where sorting is used is in maintaining database indexes. So there, I suspect there's some pretty common patterns in terms of how the data is modified that can improve sorting algorithm performance. So that's, I think, I get sort of where some of the techniques are. When you look at, and I'll put up a link to this maybe tomorrow, or maybe on Monday after break when we do kind of an overview of sorting algorithms, there's still an ongoing competition, a sorting competition that is held every year. It's called the sort benchmark, I think, and there's a bunch of different categories there, so it's kind of cool. A lot of those are focused on big data sets. So once you start to, there's these sorting problems that we talk about where we're sorting like 1,000, I think for the homework today, or on, we might be using arrays of like up to 1,000, but that's not big, right? That's not even, it's really small, right? That's like micro, nano, mini data, right? I mean, big is terabytes, petabytes, exabytes, right? And so if you're a huge cloud service and you have, a lot of these services have hundreds of thousands, if not millions of machines that are part of certain distributed services, they've got data on all of them, right? That's part of one big giant data set. Like think about Google's index of the entire internet. Sorting that becomes a really interesting challenge. And now it's not just about the algorithm, it's also about the systems and how do you move data back and forth between machines and how much of it can you do locally. And, so if you look at these systems that people have built to win these sorting challenges, it's not, I'm not even sure the algorithms are a big bottleneck at this point. It's the hardware, it's the networking interconnects. One of the categories on the sorting benchmark is for energy efficiency. Actually, there's several efficiency categories. One of them is energy efficiency. There's another one that's price efficiency. So they look at the cost of all the hardware you had to build, and it's a question of like who can find the right components and make the right trade-offs between disk and memory and CPU, and the stuff just gets really, it's just, the sorting algorithm you can think of as one point in this incredibly complex multidimensional space where it's like networking protocols that run between the two and how fast are interconnects and how fast is the processor, how much memory do you have, how fast is the memory, how much disk do you have, how fast is the disk, what type of disks are you using, how much do you spend on them, blah, blah, blah. So it becomes very, very, the winning entries in this, I think, are doing a really good job of optimizing this really, really highly complex multivariate space. And it's also changing all the time, right? And that's one of the things that's really fun about being in computer science is that, we spend some time optimizing for a particular set of circumstances, and then 2 years later, 4 years later, 8 years later, things change completely, right? For years and years, people built these systems on top of these old spinning disks, which many of you probably have never seen before and don't have any access to anymore because at some point that technology, and people spent decades optimizing for features of these old spinning disks where you literally have like a magnetic platter and it's spun. Maybe some of you still have one of these, but I'm not sure how many computers ship with these anymore. Maybe they're still out there. I haven't bought a computer with one for a long time, but they're still cheaper from a capacity perspective. You need a lot of storage, right? But that's like got moving parts, it's got geometry, right? And then so again, people spent like decades and decades optimizing for all this stuff. And then one day they're like, oh, we have these solid state drives and they're totally different, right? And they have different problems. They're not perfect either. They're expensive. They have different issues with how you manage the storage on them. But that's just one example. The other one I guess I'm thinking about recently is these new, chips that Apple's bringing out right now, right? Which look like, they're on a different performance trajectory than some of the competition, right? And so now we're seeing cases where, next, 2, 4, 8 years, we might have a big game-changing, evolution in computation again, right? Which is kind of cool. And so again, I mean, this stuff, the algorithms are a subtle problem, but the systems are never settled, because you build something and it works really well, and then 2 years later, some new technology comes along, or something gets cheaper, or something gets more expensive, or whatever, and then that sweet spot that you found in that high dimension configuration space is not so sweet anymore, right? You got to keep evolving. And sometimes the evolutions are really dramatic, right? Like a new technology comes in and just sort of flips everything around. Sometimes it's just like tweaking things a little bit, but sometimes you can imagine, you actually have to find, you're at some local maxima, and you actually have to walk down the hill before you can find a better place. So anyway, yeah, long answer to a short question, but yeah, look at Sort and look at that sort benchmark challenge, which I can, I'll find a link to that. Yeah, so they're still doing this. They have, I don't know when they put the winners up typically, but it looks like they have 2019 winners up. And you can find all the categories down here as well as past winners. So for example, the gray sort. So this was, I think, something either started or done in memory of a famous computer scientist named Jim Gray. So gray sort is, the way they measure it, this is just raw speed, right? So the number of terabytes per minute that you can sort while sorting a very large amount of data. And let's see here, it says entries must include a document describing the algorithm and the hardware in enough detail so that others could reproduce the result. Let's look at the gray winner. And then they have two categories here. I don't really, let's see here. Oh, okay, gotcha. Yeah. So and this goes down to the data dependencies, right? So the Daytona category, your sort code must be general purpose. The indie categories, there's a very specific set of data you need to sort, right? Like 100-byte records with 10-byte keys. So let's look at this 10-cent sort. This is the paper for this. What algorithm does it use? Yeah, these are, I've never looked at actually the papers. Let's see here. Algorithm. Is it merge? It says merge and sort, so it looks like there is a. Anyway, you could go through this and you might understand some of it, but this was submitted along with the latest winner, 10-cent sort by the 10-cent company. So there you go. Pathfinding algorithm. So what type of path? So we've done paths on a binary tree. If you're talking about paths on graphs, we typically don't. We don't get to graphs in 125. I had been sort of toying with the idea of maybe doing a lesson or two on them after break. The stuff that we'll cover after break will be kind of more enrichment content. I'm open to ideas about things. I thought about could do a week in Kotlin, which I'm not sure anyone would appreciate other than me. We could do, in the past, we've done a little bit more with generics, so we'll probably look at those a little bit more in terms of how to use generics and how to generify your own classes. So we'll probably do a lesson on that. We could do some stuff on threads, which are kind of fun. I've taught Java streams in the past, which are kind of neat, sort of. But yeah, I'm open to ideas. I mean, if we wanted to do a few days on graphs, that could be cool. Yeah, I mean, pathfinding algorithms on graphs are pretty cool, and they're not that hard. I mean, something like Dijkstra's algorithm has some subtlety to it, but just graph search is something that we have done in the past. And it's sort of fun from a recursive perspective. I'm trying to think when the last time we used this MP was. I think it was spring 2019. One of the MPs that we used to finish with was an MP on molecule naming. That was one that was written by Ben Nordic, one of our former course staff members, who was in biochem. And so he, designed this whole MP around molecule naming, but it was really a graph MP. It was basically about sort of identifying features in graphs. And And it was actually really fun because, I mean, I think we approach it with a little bit of trepidation because we hadn't done graphs in class, and I was kind of like, our students can be able to figure this out. But basic graph search algorithms are quite elegant when done recursively. So, are you talking about today's problem or yesterday's problem? Today's problem should. Yeah, so today's problem, the merge sort problem, I doubt that should actually, if it's timing out, it might be the problem on our end rather than on yours. If you got, I mean, we can certainly talk about how to do it. There's not much to optimize, right? I mean, if you followed the diagram, it's like, at every step your base case is, you've got an array with size 1, at which point you're done, or this, and your recursive step is divide the array into 2 parts and call merge sort. So basically, you call merge sort on the 2 parts, and then you call merge to combine the results, right? If that's what you have, then that should work. I'm trying to think of cases in which like you might be too slow. I guess one place would be making sure that you're catching the case where there's one element in the array. If you don't and you keep recursing, you'll end up with a 0 array, and that just might add a few extra steps that might slow your algorithm down a little bit. But yeah, this one might be one where I just need to let out the timeouts a little bit. That's possible. Timeouts are tough, so just a little background on this. So the way the timeouts for the problem are set is that when our problem servers boot up, they run, so the way our grader works is that we have a solution that's baked into it. And when you submit code, we compare your code to the solution in terms of its output and other aspects of its performance. And then that's how we decide if things are right or not, right? The problem occurs because when we test the solution performance, we're measuring wall clock time. And on any computer, the amount of time that a task takes, just measured in terms of, when we say wall clock, we're talking about human time, like how many microseconds or milliseconds did it take for the solution to finish the test suite. The problem with those numbers is they're really sensitive to lots of external factors. So for example, our grading servers run on shared servers that are used by other courses. To be honest, I've started, and this is just a total conspiracy theory, but I've started to think that there's a specific other course that we are sharing some of the servers with, and I think that their students are doing dumb things and slowing our servers down. Because I've noticed this throughout the semester because it's weird. It kind of like comes and goes. Like some days I'll log into our web server, which is in the same situation, and it's really slow. And I'm like, what is going on? And the next day it'll be fine. And so I have the suspicion, I should look at when their deadlines are, because I'm kind of wondering if they're like, their students are using these machines and are doing dumb stuff and are slowing down and that's the problem. Like you have a bunch of, so essentially you can think of there's some server in some data center somewhere on campus that is running our homework grader, but that's not the only thing it's doing. It's also doing a bunch of other things. Some of those things are things that we do for this class, like it might be grading an MP as well, right? Some of those things are machines that are used by other courses, potentially. I actually don't know what's hosted where, right? So I just use these machines. They run in a cloud somewhere, and I don't know what's hosted alongside them. Anyway, I'll just say that we actually don't use the solution timeout. We multiply it by a pretty big number to get a bound for your code before we grade it. But sometimes I've seen where there's a few problems recently where that seems to be a little sensitive, right? And so yeah, it's tricky, right? We're not expecting you to meet the solution performance because the numbers are too inconsistent. So I think we multiply by like 4 or 8 or something like that. And so sometimes when you hit that, it does mean that there's something wrong with the code that we can help you fix. Sometimes try it again. If it passes, you're good. There might not be anything wrong with your code, and that server just might be running a little slow today for whatever reason. So. Yeah, so good question. So there is no final exam for the class. Just let me make that clear. There's a midterm that you'll take. It's just another quiz. It's on Tuesday in the last week. So yeah, there's no final exam. There's just another quiz. And like the other midterms, each one is worth like, I don't know, 2 or 3% of your grade, some small amount. We do not have a big high stakes exam because I don't believe in big high stakes exams, because what people do is they cram and they forget everything the next day. So that's not how we work. Most of what you learn in the class, by the time you get to the midterm, you've already learned, right? We don't expect you to suddenly make this last ditch effort to learn everything in the last week, because again, you don't retain stuff that way. The last midterm, yeah, we'll be asking questions similar to the kinds of homework problems that you've been doing recently. And you're right, and those are questions that build on a lot of concepts that we've seen throughout the semester. So we expect you to be able to do some OO, right? Some object-oriented programming. We'll expect you to be able to write some iterative code. There will definitely be questions on recursion on the last midterm. There will be questions, I'm trying to remember what we've used in the past. I mean, anything's fair game. That's, anything that we've touched on through the semester. But on some level, I mean, I think the focus is still on the types of problems that we've been solving over the last, the third half of the class. But again, those are problems that, we now expect you to be able to design classes without us having to babysit you or whatever. I mean, a lot of things we've been doing recently are just like static methods, so that's fine. Those are, just like writing a method. But yeah, like anything is fair game, right? Could see some OO, we'll definitely see some recursion. We'll probably see something on sorting. That's kind of a classic, is to ask some type of sorting question. So those are good things to look at. Yeah, so it's anything is fair game, but the format will be the same as the previous midterms as well. Yeah, so I'm planning another extra credit opportunity. I'll talk about that after break. Something I need to work on a little bit next week, just to sort of do some final preparations on. And I think at some point we'll get a grade book up. That it's we're close, right? It shouldn't really take that long at this point, but yeah. So the extra credit is something we're planning. The grade book will probably get done just because I'll finally have some time over the break to get around to doing the UI for it. The data's all there. It's just a question of kind of collecting everything and having it look nice. But yeah, and the extra credit opportunity, I'll reveal more about that when the time is right. But yeah, it'll be maybe one extra percentage point still available. Good question. I think, last semester's MPs, you could certainly, trying to think about how we distribute. So last semester we used a similar project type approach. The code for that's available. I don't know, it's not being maintained, so I don't know if it still works. It probably does. So you could certainly, I think the GitHub Classroom invitation link that we used might be down, but I could certainly just, we're not going to, that's a great point. We're not going to use that MP again. So I should probably just put it up somewhere publicly so that people can get at it. The testing works the same way it does this semester, where there's no hidden testing. So the test suite that you get with the MP is the same thing that we would have done officially. So I'm not going to burn any more cycles on our servers grading those old MPs. That's been turned off. I think so. Yeah, it has. But I would certainly be happy to just put that up where people can clone it and get at it and do the work themselves. And if you pass all the test suites locally, then you would have passed them remotely. Yeah, try the link. I think it'll probably kind of set up something on GitHub Classroom, but because we're not using, I hadn't thought about this before. Because we're not using that MP, that's kind of a nice feature of it, right? Our new model going forward is that we'll probably be developing a new machine project every year, and then we'll use that for 2 semesters. And so probably what we should be doing is just kind of notifying people after the year is up, because we don't want people publishing their code initially because we're concerned about cheating. But once the year is up and the MP is cold and we put that one away, we might as well just put it up publicly and let people go at it, and also be able to kind of do some like to do it on their own or publish their own code somewhere. Good project for the winter? Could be. I don't know. It depends. I mean, post on the forum about winter projects. I mean, I think we'll all be doing fun stuff over the winter. I have a couple of cool things that I'm planning to work on over the winter. Improvements for the class. So I'm always pumped to have. I mean, I get tired during the semester. I mean, just pumping the content out for the class, just keeping things running is kind of exhausting. So I look forward to. Usually it takes me a few weeks just to recharge, but then I get the itch again and I want to do some hacking. So I've got a few little side projects, and there's like an extra week, between semesters, and so that's always enough time to make me feel like I can be dangerous again and break some things. As far as projects, I don't know. I mean, I tend to think when you're getting started, it's better to rotate. Don't do too much of one thing. I mean, if you really love Android development, okay, fine, right? But I think you'd probably learn more from like doing your own project. Where you started on your own, maybe do it in Kotlin instead of Java. So Android itself is really trying to move developers to this new language, which I'm a huge fan of. So that's another option. Maybe do some back-end development on your own. When you're getting started, on some level, there's no wrong side project to work on, but you also want to think don't get too comfortable, right? I mean, at some point, you're going to get a job, and your job's going to involve kind of getting very good at one particular thing, right? That's how people, achieve excellence in things eventually, is that, you sort of like focus on one thing. It's like you're going to get known for doing one thing. And so you get good at doing the things that you need to do that one thing. Right now, as a student, you don't have that requirement. Like, you can freelance, right? So, and I think it's hard because it's like, oh, I just felt comfortable with Java and Android, and now you're telling me to do something totally different. It's like, yeah, so what? Like, you'll figure it out. It'll be fun, right? And then you'll have something new that you learn. And if you can do that often enough for a couple of years, you may find something you really enjoy. You may find something you're really good at. Or once you go out and look for a job, now you have a broader base of skills that you can, share with employers. And so they're like, yeah, I can do that. It helps to be able to show that you're adaptable, right? Like, if you get really laser focused on one thing, then you get to industry or you're looking for a job, and people might think, well, that person only seems to be able to do Android apps, and we don't need someone to do Android apps. We need someone to build a cross-platform app in React Native. And so it's like, you don't want to like shoehorn yourself a little bit. Other questions? Yeah, building websites is fun. It's one of my side projects in the next couple months. I want to get a blog going. I've been talking about this for a while, but I think I'll get there. Next semester, I'll be teaching 125 again, obviously. I think that some of you will be involved in the class as course staff, so I'm looking forward to that. I am offering, now, so the calculus around this is a little more complicated than it was in the past. So I'm offering like a 1-credit pass-fail. I need to make sure that's set up properly in the course catalog, by the way. Like a 1-credit pass-fail side course on Kotlin. Kotlin is a new programming language that interoperates with Java. It's a beautiful language. It's a huge amount of fun. It's the language that I use for as much of the course infrastructure as I can. Our auto-grading tools are all built in Kotlin. The homework tool is built in Kotlin. The playground backend is built in Kotlin. I mean, it's a really, really fun language. So I'm planning on teaching a side course in that. I have some materials already prepared, but I think probably what we'll do is do a little bit of sort of just getting up to speed with the language, and then we'll do like an Android project in Kotlin. And what we may do, just because I already kind of know a little bit about how to approach it, is we may take this semester's MP and rewrite it in Kotlin, both the front end and the back end. And we may actually do the back end in like a little bit more of a normal way where it's not like baked in to the app. It might be like a separate folder in the repository that runs a little bit differently. So that's this little sort of side course I teach in the spring. Particularly and we'll talk more about this after break and over the coming weeks, particularly for people who are interested in the course and contributing as course staff over the next couple semesters, we're starting a conversation in the department about moving, well, it's got some exciting changes afoot here. So there's a set of curriculum changes that are coming into place next fall. That's going to introduce this new course 128 as a follow-on to 125 that'll be for all majors. 125 is going to drop down to 3 credit hours, and actually 125, for that reason, is no longer going to be 125. It's going to be 124 because we had to renumber it. So all of my branding for 125, including this neon sign that I spent $1,000 on, it's all... Anyway, we'll keep it around. I think we'll just make a small edit. So as part of that, and we're kind of drifting in this direction, we're talking about rebuilding the course to use Kotlin. And I have a bunch of reasons for that. So one of the reasons I'm teaching that side course is to try to prepare staff and start to let people get some experience in the language. I certainly know the first week that we do it, it's going to be rough. The first semester that we do it, it's going to be rough. But but that's anytime you change languages, this is what happens, right? I'm teaching people Java one semester, and then the next semester I'm teaching them something else, and so the staff will have 1 or 2 semesters that'll be a little bit rougher than usual, just getting people accustomed to the new language. But it's a great language, and it's just really going to improve the course in a variety of different ways. I don't know what people are saying no about. The number? I don't know. I mean, I don't know how I feel about the number. Obviously I've been doing 125 for a while, so I'm sort of semi-attached to it, but 124 is acceptable to me. And it wasn't really... I was trying to hang on to it, but there are university reasons why this needs to happen, and the benefits are that we get to do this whole new thing, right, with a restructured curriculum that I think is going to be really exciting and going to be really beneficial for students. So the course number was a kind of a small price to pay for that, and plus, like, all the 125 swag you guys have or whatever, like that'll serve to identify OG staff and students for at least a couple of years. So anyway, that'll be that'll be the spring, right? And so if you want to learn Kotlin, you have some time in your schedule. It's certainly not as structured as this class is. A lot of the materials are still online. The workbook, so on some level, the workbook format that we've been using this semester is something that I kind of prototyped in the Kotlin course last spring. One of the things that I may start hacking on over break is adding support for the homework problems that we've been doing, because we're going to need those eventually. I'm not sure we'll have it for spring, or it might be partially working, or I might just have a few of them. But by fall, the idea is to keep the same format for the class with the daily lessons, daily homework, but have it in Kotlin. And so that the homework system that we have right now should be able to support Kotlin, but there are some differences between the two languages that we're going to have to figure out how to accommodate. It should not be... the Kotlin course is... It's in the catalog. It's at CS 199 IKP, Introduction to Kotlin Programming. So it's in the 199 group. I've got a few minutes left. Have you been on startups? No, I've never been involved in startups. I think for young people, startups are awesome. I think it's a super exciting thing to do. I mean, the trade-offs there are sort of obvious, right? It's like, if you go take a job at Microsoft, like the heat death of the sun will occur before Microsoft goes out of business, right? Is it a particularly exciting company to work for? I think it depends. I mean, it's really hard to say something categorical about an entire company like Microsoft or Google or Facebook even, because they do a lot of stuff, right? There are probably engineering teams at Microsoft that are incredibly fun to work for and are doing really cool things. And then someone's got to maintain Clippy, right? So or whatever the equivalent of Clippy is. So there are many, many different jobs within those companies. Some of them are probably more exciting than others. Startups, on the other hand, there's no stability. That's the point, right? You want to be, you're taking a risk, right? you're becoming involved in risk, and some of those risks pay off, right? I mean, I knew people who did startups, who walked away with a pretty good chunk of change at the end of the day. So I think it depends, right? But I think when you're young, it's like if you were going to do a startup or get involved in one, I mean, this is why a lot of people in their 20s and 30s, tend to get involved in that type of thing. What's interesting is it turns out that, just so that I don't sound ageist here, it turns out that apparently when people studied this, they found that startups with older co-founders tend to do much better. So take that what you will. So maybe you want to join a startup, but if the startup co-founders in their 50s, like, don't let that turn you off, because those people have a lot of wisdom. They don't always have the same appetite for risk that a 20-year-old has, but they usually know a little bit more particularly about the sector that they're trying to get started with. Again, I mean, startups, the idea, I think, of working on a small team with people, you get to do more, you get to touch more parts of the product and the infrastructure, you're more involved in the day-to-day sort of decision-making process about how things work. It can be tremendously fun. And I think it can help you learn a lot more, broadly speaking, right? It's like, if you go work for a big software development company, like, you have a very specific role to play in that company. And then there's other people that do all sorts of other stuff, right? So you don't have to deal with HR or with, advertising or whatever. And I think with startups, people tend to get pulled in a lot of directions, and they see more about how a company works, right? Because it's like, we don't have an HR department. There's just, Craig, and Craig needs your help with hiring, because it's like when you go work a startup, if you're interviewing people, like, if there's 5 people at the startup and you're hiring person number 6, there's no HR department for them to do, to talk to. It's like everybody's involved with more stuff. Clippy, yeah. Clippy. Well, I don't even know. I don't think Clippy. So Clippy was like the assistant that used to pop up in Microsoft Word when you needed help. I think it's something different now. There were a lot of memes about Clippy. I mean, and I guess I also don't mean to like throw shade at anyone who's working on that type of thing, but there are legacy software products that, I guess I would not feel as excited about working on. But that's just my preference, right? Again, like I said, even a company like Facebook, where you might say, I don't know if I'm even on board with the core mission of Facebook at this point, but they still do some really cool stuff, right? There are still people there doing some really interesting projects that don't necessarily all relate to their core business of whatever their core business is. Selling ads, I mean, that's what their core business is. So CS199 IKP. Yeah, you got to get in the right section. So that's another case where the section. So 199, just so people understand this, 199 is this sort of like, it's sort of our prototype area, right? It's where sort of prototype one-off classes end up that don't have an official number. So that's why 128 is there next semester. It's the first time that we're offering it. Non-major graduates, yeah. I mean, we have openings for course staff that are open to anybody who's taken the class. So anyone can sign up to be a course assistant, and it's a role that we will train you to do. So we have a great training program that's run by designed by one of the head CAs that will we'll put you through, and then you get practice doing it, right? In a really supportive environment, right? I mean, that's the nice thing about having a couple of levels of staff, right? Is that if you're an assistant and you're having a hard time helping somebody on the help site, there's also associates that are on there as well that might have a little more experience or seen that problem before or whatever. So yeah, and course development, that's something that's been a little bit of a sort of a rockier road for some people. We have had students get involved in course development, and I'm always hoping that people will. One of the challenges is, unfortunately, like, some of the things that I need people to be able to do are not things that we teach, at least not right away, right? So for example, web development is a huge part of what I have to do in order to maintain the class, and there just aren't a lot of people that come with that skill. You can take a class at the 400 level and learn it like as a senior, right? But at that point, it's a little too late. So some of this stuff is sort of things that you just kind of have to learn on your own. I guess I wish we taught some of this stuff more, particularly early on, but we don't. So, all right, I'm past time, so I'm gonna pause the questions stream, and apparently Dogger wants to update too. Okay, go for it. But yeah, no, I'll be back tomorrow. We'll do Quicksort, and I'll take more questions. So I'll see you guys then.